Grade 11s. In our last lesson, we took a look at kinetic molecular theory and intermolecular forces, which are the forces between the molecules, to explain gases. In this lesson, I want to explain solids and liquids. From previous experience and classes, you understand that solids have a definite shape and volume and cannot be compressed. Liquids do not have a definite shape. They will take the shape of their container, but you can measure their volume. They also cannot be compressed. The question that we need to answer is why. Before we go into an explanation of the why behind things, I'd like you to read in your textbook pages 416 and 419. Both gases and liquids can be described as fluids because they can be poured and they can also diffuse. When we know that means that they can go from areas of high to low concentrations. Some liquids, and gases for that matter, flow more easily than others. This is measured as viscosity, which talks about the resistance to flow, or the stickiness. If you imagine trying to pour syrup versus water, syrup is much more viscous. The reason that some fluids pour more easily than others has to do with things like the surface tension, which is the attraction of molecules between each other on the surface of a liquid, and adhesion, where the molecules in the liquid or the gas are attracted to the container they're in, and cohesion, which is an intermolecular force between the molecules themselves. Take a moment from your textbook to write a quick definition and answer these questions. A great demonstration that you can do at home to experience and visualize adhesion and cohesion and surface tension is to take a dropper, any dropper will do, and some water, and try to see how many drops of water you can get to sit on a penny. If we take and put drops of water on the penny, what you notice over time is that we end up with a large clear bubble on the penny. See how many drops that you can get. You'll probably be surprised at how large of a bubble of water you can make floating on the surface of the penny. The reason for this is there's a large amount of surface tension on the surface that allows the outer edge of the water to act like almost a shell to hold it in. Also, there is a lot of attraction between the water molecules themselves. This is called cohesion. You may also try to take a long, narrow container, like this graduated cylinder, or any tall, skinny container you might find in your home, and fill it partway through with water. When you do this, take a really close look at what the water is doing at the edge of the container, where it meets the glass. If you take a really close look, you will notice that the water appears to rise almost up the glass itself. This is because the water is adhering to the glass itself, and it's called adhesion. From the side, if you're at eye level and taking a look at it, you would notice that you could take the reading of the water at the top or the bottom. At eye level, it will look almost like there is a bubble. Clearly from this cross section, you can see that the actual level of water in the container has to be accurately measured from the bottom. This is called a meniscus. Anytime we measure the volume of liquid in a tall, narrow container, we must always measure to the bottom of the meniscus because of adhesion. Liquids, just like gases, are also always moving. They will bounce around, but they have less kinetic energy than you would find in molecules of a gas. Also, the forces that hold together liquids, the intermolecular forces, are typically somewhat stronger than they are in a gas. So it takes more energy to separate the particles far enough to be called a gas. When liquids are bouncing around past each other, the intermolecular forces tend to try to pull the gas particle or the liquid particles back together again. It's almost like imagining that the particles of or the molecules of a liquid are held together by weak elastic bands. If you apply enough pressure, you can snap the elastic bands and the particles will separate enough in order to be called a gas. But unless you apply enough energy in the form of heat, the molecules will always snap right back together. In a liquid, the particles are always touching each other. Though they may separate small amounts, enough for them to roll past each other and fill a container, they will still, in general, remain touching. We can imagine the particles in a liquid to be like a container full of marbles. As you tip the container, the marbles can roll past each other, but they will remain touching at the same time. Now, every once in a while, when particles are vibrating around in the liquid and rolling past each other, they will hit each other hard enough for one of the particles to be kicked out of the liquid and take off in the gaseous form. We could imagine that one of the particles, as it bounces around, gets kicked off and is taken off as a gas. This process is called vaporization if the container is closed, if it has a lid on it. If the container is open, we would call it evaporation. In the example I just did, this would be evaporation. The particle is free to leave the container and take off into the atmosphere. If I put a lid on my container, the particle, when it bounces out of the container, will end up bouncing around in the upper part. It is still existing as a gas, but is now putting gas pressure on the container. The more energy I apply, the more particles that can leave and join it and cause increased pressure. There is a point where we have hit the maximum amount of pressure that we can inside that container. Both evaporation and vaporization are called cooling processes. This is important. We call them cooling processes because the highest energy particles are the ones that leave the system and take the heat with them. Each particle, as it started to vibrate, was acquiring heat energy. So as the particles vibrate more and more and acquire more and more heat energy, at the point where they'd be vibrating enough to actually raise the temperature in the thermometer, they actually have enough energy to escape the intermolecular forces and take the heat with them. I mentioned that there was a point where the particles leaving the system created enough pressure that they had reached a maximum. At that point, every time one of these particles gains enough energy to go up into the liquid to vaporize, another particle ends up being forced back down into the liquid and is condensed. For every one particle that goes up, another one will come down. This process happens at equal rates. For one that goes up, another comes down. Because it happens at equal rates, we call this an equilibrium. The term dynamic means that this continues to happen. The motion is continuous. So at a certain point, the vapor pressure in a closed container will remain a constant. What happens if I increase the temperature? Well, if I increase the temperature, then the molecules vibrate faster, so we can actually have more of them up here vibrating at the same time because they are vibrating fast enough to stay in the gaseous state. But even then, eventually, enough of them will get close enough together that they become the liquid state and fall back down into the solution. So when we increase the temperature, the vapor pressure will increase. If I cool it and the particles move more slowly, the vapor pressure will decrease. In a container of liquid, when we have particles starting to form a gas, they can form a bubble under the surface of the liquid. This bubble forming under the surface of a liquid has vapor pressure. It's vapor pressure because it's still under the surface of the liquid and is not yet exposed to the air. Air pressure is still pushing down on the surface. At the point that the pressure being caused by the bubble, the vapor pressure, becomes equal to or greater than those pressure from the air pushing outside the liquid, the atmospheric pressure, the bubble can escape. At the point where the vapor pressure is equal or greater to the atmospheric pressure, we call this the boiling point. Because boiling point is dependent only on the pressure of the molecule under the surface and the air pressure above it, we can actually make liquids boil at any temperature by changing the amount of pressure above the surface of the liquid. So boiling point happens at that temperature where vapor pressure is equal to atmospheric pressure. Why then do we say that water boils at 100 degrees? This is the normal boiling point. Water boils at 100 degrees at 1 atmosphere of pressure at sea level. When we consider there are two little individuals, one at the bottom and one at the top of the mountain. The individual at the bottom of the mountain, if he was trying to boil water in a pot, has the entire column of air above him pressing down on the surface of the liquid. And we know that at sea level, it takes 100 degrees Celsius worth of heat, energy being put into it to get the particles vibrating fast enough to escape. The gentleman up at the top of the mountain has only a small column of air pushing down on him. It takes much less energy for the molecules to escape. The temperature on the top of the mountain might be boiling as low as 50 or 60 degrees Celsius, depending on your elevation. Because the temperature can get so much warmer at the bottom, a substance cooking in a pot at the bottom would be cooking at 100 degrees Celsius, and a substance like noodles or eggs cooking in a boiling pot up at the top of the mountain would only be cooking at 60 degrees Celsius. Although the water boils at a lower temperature here, because it's boiling at a hotter temperature down at the bottom, the substances will cook faster. Boiling is also called a cooling process. Picture a pot of water. Under this pot of water, we're going to add a fire. The particles of water inside the pot start to vibrate and eventually gain enough vibrational energy that they can start to escape. We have boiling. Even though heat continues to go into the water, the temperature of the water never changes. At sea level, it remains at 100 degrees Celsius. Why will the temperature of the water not go up, even though we continue to put heat into the water? It continues to go up because any particle that warms up to the point where it can overcome that vibrational energy leaves and takes the heat with it. This is why we call boiling a cooling process. Particles with enough energy to escape the system leave and take the heat with it. Solids are the lowest kinetic energy state of, when we talk about the three main states of matter. In solids also, particles continue to move. But now the particles will just vibrate around a fixed point. Basically, they stay where they are and they shiver. It is for this reason that solids will not flow. The particles cannot roll past each other. They're just vibrating right where they are. This is also why solids have a fixed shape and a fixed volume. Because they're not moving around, they will not change where they are and the shape will remain constant. At the point that I give the particles inside a solid enough kinetic energy, if I increase the kinetic energy by warming them, they will eventually start to vibrate fast enough that they can roll past each other and flow. We call this melting. If I remove energy and the particles start vibrating back on the same spot, we call that freezing. The melting point is always the same as the freezing point. Water melts at 0 degrees Celsius and freezes at 0 degrees Celsius. In general, substances that are ionic have higher melting and boiling points because the forces of attraction between them are so strong that it takes more energy to make them melt or boil. Consider salt. If you've ever poured salt into a hot frying pan, it does not melt. It's because it is an ionic substance. Covalent or molecularly bonded substances like sugar will melt at much lower temperatures. It's also important to note that not all substances freeze or melt. Wood, for example, if we subject it to enough heat, will eventually just react with the oxygen surrounding air and undergo a chemical reaction. There are now several other states of matter that have been identified. Plasmas are one that you may see inside of a fluorescent light or a neon light, or when you look at the sky and see the northern lights. There are also states of matter like Boise-Einstein condensates, fermionic condensates, and quantum spin liquids. But the three continuous states of matter that we influence commonly in the chemistry lab by changing the amount of heat energy we apply are solids, liquids, and gases. The changes in state as we move from solids to liquid to gas are physical changes. We are changing the spacing and the movement of the particles, but not the nature of what they are. Any change in matter where we're putting heat into the substance is called endothermic. In order to make a substance melt or boil, we must put heat into it. It is an endothermic reaction. Therefore, the reverse must give off heat. These reactions are called exothermic. Extra heat is given off. If melting a substance or boiling it requires us to put heat in, then when substances condense or freeze, heat is given off. There are names for the phase changes as substances move from solids to liquids and gases in reverse. When we have a solid changing into a liquid, we call that melting. For example, when ice melts to form water. As a liquid changes into a gas with a continual increase in heat, we would call that evaporation in an open system or vaporization in a closed system. The reverse process as a gas turning into a liquid is condensation. You may see condensation on the outside of your glass in the summertime when the energy in the air is removed by the cold liquid and the water in the air condenses back. When a liquid changes back into a solid, we call that freezing. Another name for freezing is solidifying. Some scientists prefer to use the word solidifying because in English the word freezing also implies that it's cold. But iron, for example, freezes, turns back into a solid at many hundreds of degrees Celsius. It is clearly not cold. Under certain situations, we actually can have gases and solids go back and forth between their phases without ever becoming a liquid. When a solid goes directly to a gas without ever becoming a liquid, this is called sublimation. In the wintertime, when you have frost on your windshield and you turn the defroster on, you notice that the frost leaves your windshield, but you don't ever have water dripping down the inside of the windshield. The water is going directly from its solid phase to its gaseous phase without ever being a liquid. It is subliming. The process of frost forming on the windshield, for example, when you're riding the bus and you take your warm breath and blow onto the window to make the frost appear, the water vapor, which is a gas, goes directly onto the window to become a solid. It never was a liquid. This is called deposition. This happens in the wintertime also when it snows. Snow has gaseous water vapor in the air, congealing into a solid form of a snowflake. Hopefully at the end of this video and the lesson that follows, you can explain the difference between solids, liquids, and gases using molecular theory. There's a variety of terms that you need to understand and be able to describe. I also find it important that you understand the difference between boiling point and normal boiling point, and understand why boiling and evaporation are considered cooling processes. To help reinforce what we have learned about solids and liquids and gases in terms of how their molecules are moving and how closely packed they are, I will get you to do the worksheets in your blue work or your green workbooks on pages 23 to 26.